Hello, everyone. My name's David Brooks, and I'm here in Classical Mechanics 2, Georgia Tech Spring 2019, and I'm here to just run through a quick problem. It was assigned to us as problem set 3, question 5, if I'm correct. And the actual setup of the problem is fairly straightforward. The basic idea is we're looking at the Earth, and we've drilled a hole in the Earth from one side all the way to the other. And the hole isn't necessarily on center of the Earth. And we've dropped some mass from one side, and we're going to assume that it goes into the Earth and moves with some motion within there. And the basic idea is to find not only the motion as it moves around inside, but also the time it takes to move from one side of the Earth to the other. We've got a few assumptions we can make right at the top. It tells us that we can say the density of the Earth is 5.5 grams per centimeter cubed, and it's constant. And it said that we can ignore friction in the problem. And we're going to go ahead and say another thing. I'm going to assume that the thickness of this tunnel, the radius, is small enough that it does not appreciably affect the density of the Earth. That is to say, we don't have to worry about this no longer being a perfect sphere. Ignoring my drawing skills. So, what we need to do to begin with is to draw out the problem a bit more meticulously. Ooh, that's not a very good sphere, but we're going to have to live with it. So I'll call the center of this sphere right here. And I'm going to say that this line, again, we're assuming that the hole is of negligible radius. So this line I'll take as the x-axis, positive direction being over here. And the x-axis, of course, extends all the way as far as it needs to. I'll also take this vertical axis running through the center of the sphere. I wish that was a bit more vertical. I'll take this intersection right here to be x equals 0. And our mass m sits on some position x along this axis. It has some separation from the center, r. This, of course, forms a right triangle, with this value just being the x value of the triangle, of the mass, rather. And this is a constant that was defined when we drilled the tunnel. It wasn't given to us, so I'll just say that it's a. And so we've got a pretty solid setup right now. We know that this mass m will experience some force of gravity in some direction, and we can easily define where it is in terms of these ideas. In fact, I'll go one step further. I'll call this angle theta. Angle theta right there. Now, in order to make this problem possibly significantly easier, I imagine you can set up some complicated integral to figure out where exactly the force is pointing, or how each little dv of this sphere interacts with the mass. But there are a couple simplifying ideas that we've already learned that can make this problem a lot easier. The first is one that we discussed in class, and it is, if you are a point mass, and you're interacting with some sphere, so let's call it a sphere of mass m, big M, we can model this. I'll draw a line here, so you know it's a different situation, as simply you interacting with another point mass of mass m that was positioned at the center of this sphere. That is to say, this sphere interacts with me in precisely the same way this point mass does, given this point mass is where the center of the sphere would be, and the two are of the same total mass. Another simplifying idea, and this is one that we showed in problem 3 of the same problem set, if I'm not mistaken, is more spheres here. I'm really glad I'm good at drawing those. Another simplifying idea is if you're a mass inside a hollow sphere, it doesn't matter where in the sphere you are, the net force on you is 0. And the sort of qualitative reasoning for that is if we take some dm of the hollow sphere here, and we draw a sort of solid angle, something that looks a little bit like that, we get a corresponding dm over here that its gravity would be pulling on you in exactly the same but opposite way this one does. And so ultimately the net force is 0. And these two combined make our problem a lot easier. I'll draw it over here, I suppose. You see, ooh, that's a bad sphere. We are in this sphere at some point, at any given time. Here's the center of the sphere, and here's the separation r. Now, if we draw a concentric sphere, also with radius r, ooh, imagine that's a concentric sphere, then what we're really dealing with is two spheres here, one solid sphere that we're on the outside of, and one hollow sphere that we're on the inside of. It's basically these two situations sort of superpositioned, if you will. And so the basic idea is, as we move through this sphere, as we move across the x-axis, we start out with some behaving as though we were on the surface of some smaller sphere like this, and then we move to behaving as though we were on the surface of an even smaller sphere, and then as we cross x equals 0, it looks like we're on a bigger sphere as we move out further here. So, this is all we really need to know in order to get into the nitty-gritty. Of course, this assumption only works because this hollow sphere that we're inside doesn't interact with us at all. It's only the sphere that's below us. It's only the sphere that has a radius of r that interacts with us. And so we can start making some real work done here. Firstly, we know f of g, that is f of gravity, has to be g m1 m2 over r squared. And we also know that it's in the r hat direction. That is to say, we're being pulled into the center. The force is moving along this r that we've defined there. But we don't want that. Again, we noted that we can ignore friction, and we've confined this mass to moving only along the x-axis. We don't care about force in the vertical axis, only the horizontal. So, the force that we actually care about is going to be Fg times SOHCAHTOA sine of theta. So, what we care about, F, is therefore, let me move this up a bit, is therefore G m1 m2 over r squared sine of theta. Sine of theta in the x direction. Now, if we just take m1 to be our mass m, we need to take m2 to be the mass of this shrinking or growing sphere that exists below us. And so what that's going to be, it has to be the density of the Earth times the volume of whatever this sphere is, V of sphere. And V of sphere, as I'm sure we're all aware, is 4/3 pi r to the third. That's not a very good pi, but you understand what I'm saying. So if we sub that into this, that means F equals gm, and then we've got the quantity 4/3 pi r to the third divided by r squared sine of theta. This r squared and this to the third will cancel. And we can do you one further, because we'd like to get this f in terms of x alone. We know from up here, we know from this triangle we defined, sine of theta equals x over r. Sine is opposite over hypotenuse. So this is simply gm 4/3 pi. Ooh, I've forgotten a row. We can add that in now. 4/3 pi r rho times the quantity x over r. This x and this r and this r rather will cancel. And so we get gm 4/3 pi rho x equals mx dot dot, because as we know, f in this x direction that we've defined up here, f is equal to ma, Newton's law, easy peasy. So this m and this m have to cancel. And I'm sure we've all seen this differential equation before. X dot dot equals a cosine root 4/3 pi rho t plus b sine root 4/3 pi rho t. If we plug in the initial conditions, x of 0 equals some constant, because we know when we drilled this hole, the distance from x equals 0 out to where the hole is, this distance was just some constant that was defined when we drilled the hole. We can just name x of 0 equals to c. And of course, doing the math here, you might already see it. A equals to c. And the problem says we dropped the ball. We didn't, the mass, or whatever it is, we did not give it an initial velocity. We only dropped it. So x dot of 0 equals 0. And the derivatives here, cosine goes to sine, and sine of 0 is 0, so this term goes away. Sine goes to cosine, and so this term goes to 1 when t is 0. And so we get something along the lines of b 4/3 pi rho equals to 0. And since this is all constant, we know that b has to equal 0. So we have our expression for, this is incorrect, by the way. This should not be x double dot, that's just x. And so we ultimately get the expression x is equal to c cosine 4/3 pi rho t. But how long does it take to get to the other side? Well, if we said it's at one side when t equals 0, that means it has to be on the other side at some time t naught. When t equals 0, cosine equals 1. So by some level of logic, when we're at t naught, we have to be on the other side. X has to be c, but in the other direction, so it's negative c. So it stands to reason that cosine of all of that stuff we just figured out has to be equal to -1. So at t0, cosine of root 4/3 pi rho t0 is equal to -1. And just a little bit of math away, we know that cosine, of course, goes to -1 when its theta is equal to pi. We can see that t0 is equal to pi over root 4/3 pi rho. And we have a constant defined for rho. Everything else is a constant. Of course, if you feel like, you can figure this out numerically. I get that this is approximately equal to 2,534 seconds, give or take. But that's all I had. I thank you very much for listening to all of this. I hope you all do well in future physics exams. Thank you.